Yeah. Welcome. My name is Roy Smith, Manager Technology of this pilot plant at Royal Divers Wiener here in the Netherlands. This is food for thought session number, I don't know. At least welcome, and today I want to talk to you about ball mill refining. So when you come to refining into the cocoa world, it's more of grinding. You grind cocoa nibs to a cocoa liquor, which can be done by ball mills. And ball mills can also be used in the chocolate, compound, fillings, bread spread industry to refine, and mostly then you refine the sugar particles, and if you make a milk product, your milk particles into the fineness you want to have. Now, this is more of a batch or a continuous system, and today I want to explain to you about how a ball mill works. We've put up this line here in the pilot plant with our small ball mills to show you how a line works like this. And then with Dennis later on, he will explain to you how the whole system works. So in general, you have a ball mill where a ball mill will, you start of course with a mixer. You mix your ingredients, you make a recipe. You have for chocolate your cocoa butter, your cocoa liquor, your sugar, your milk powder. And we filled it up with milk chocolate in this case. For ball milling, then you mix it into a homogeneous mix. Then you pump it through the ball mill and you refine it. Now, a ball mill system can work with any kind of recipe as long as you have a fat content which is over 30% fat. Then it will run perfectly in a system like this. Now you can see already the product is going out, and when we follow the line we end up in the last part where we have Dennis.
Hello again.
Welcome here.
Thank you.
In the pilot plant, in your pilot plant basically.
My pilot plant, yes.
Dennis, can you please explain us the
Yes.
principle of a ball mill? How does a ball mill work?
So in basics it's a vessel filled with metal balls. So we got two up here. Well, these ball mills have two sizes. So the first one, because you have coarse product going in, you need bigger balls to break those particles down. So you have 9.5 millimeter balls.
You want to have bigger balls?
I want to have bigger balls.
Okay.
Now, when it comes out, it's already around 50 to 40 microns from the first ball mill. So the passage, we call it, one passage, goes through the ball mills. When it comes out, it's already around that size.
So typically, what is your mix? So we have a mix. What is your fineness in your mix?
So a standard fineness of a mix is around 500 to 600 microns.
Okay.
On average.
On average.
Then it is slowly by gravity it comes into the first pump, and the first pump is the part where we start putting up the pressure of the product into the first ball mill.
Okay.
So the product comes into the ball mill from the bottom.
Yeah.
Now there are all these balls inside which weigh down on this product, these balls, yes, and you get a counter pressure. So the balls press down and the press of the pump comes from the bottom. And so then in the middle,
so you have the gravity is the force down, the natural gravity force down. Okay.
Correct. And the product pushes up this package of balls a little bit, so the balls do not stay on the ground, because then you grind your ball. You don't want that. So they push it up a little bit, and then the shaft in the middle that turns around really fast. Now we put it on slow because otherwise we cannot talk to each other. But it turns around really fast, and because of this movement and this counter pressure, the balls are rotating and hitting the particles coming in between the balls. Okay. So, and that's how we refine the product.
Okay, so the product lift the balls.
Yep.
They're more or less like floating.
Yep.
And then you rotate.
Yeah, and because of this rotation, and the balls are pretty compact, right? So it's not like they are there's a particle
floating
here and
okay,
here.
yeah, yeah.
They have to be close to each other to be able to refine.
Which is in the vessel. Okay.
Exactly, correct.
Yeah.
This vessel is heated, but when we start to refine, we can start to cool.
Okay.
Because during refining, a lot of heat releases, so then
which
we cool.
is the result of refining.
Exactly, exactly.
Okay.
So then we need to cool because a lot of our ingredients can burn and we do not want that. Also,
especially with milk particles or the lactose, the whey particles, they are temperature sensitive. So we need some cooling as well.
Some special ingredients that don't do too well on heat. So, so like I said, from the first ball mill, product comes out at around 50 to 40 microns, depending on your starter mix. And then we go to the second ball mill, which holds smaller balls.
Okay.
Typically, in our case, 6.3 millimeter balls.
Okay.
Now, why do we have smaller balls? Because from the first ball mill, we have fine particles coming out.
Yeah.
So now we don't need those very large balls to hit them. We need some fine refining with some finer, delicate balls.
Now you need small balls. Okay.
Yeah, exactly.
So again, the same system?
The weight is completely the same for the amount of balls. That doesn't matter. It's about the size of the particles going into the second ball mill.
You want to have the counter pressure again.
Exactly. So product again is loaded into a pump. The pump puts on the pressure on the package of balls with the product. And again, the shaft is rotating really fast to refine the particles.
Okay.
Same principle, just a finer product. And it's something I can show you later on in the lab.
Yeah.
Now the second ball mill, usually your fineness should be between 20 to 25 microns.
Which is the industry standard, which is normal. Can we go finer if we want with a ball mill?
Yeah, for sure. There are, of course, a couple ways to do it. Maybe you have one ball mill and you circulate a lot of time and then you have a finer product. Or you put in a third one. What you can also do is reduce the pump speed. So you feed your product slower to the system. That means that inside of the system, chocolate remains for a longer time, which also means, again, that you refine more. So there are a couple of ways to do it.
Yeah, well, that was one of my questions. You're a bit ahead of me, but what are the controls? Well, so I understand now that the operator can control the speed of the pump.
Yeah.
And by controlling the speed of the pump, he controls the retention time of the product in the vessel. And by a longer time it gets finer, by a shorter time it gets coarser. Yeah. Okay, so that's how an operator controls. Are there any other things?
Well, of course you could adjust the shaft speed, but there is a minimum and maximum speed because at some point you run so slow there are no more contact points between the balls, so you don't have a lot of refining. Oh. And if you go too fast, the package of balls, it's no longer moving around in the package, but just circling around, and then you don't have any refining. So there is a maximum and a minimum of speed. So you can play around with the pump speed much more in this regard to do something with fineness and capacity. Okay,
so then now we come to the testing part. You said you can show us what happens in the in terms of fineness?
So I took a couple samples. I took a sample of the pre-mix, so the mixer without any refining. I took a sample from the first ball mill and a sample from the second ball.
Okay, well.
And then we can go to the lab and see.
Let's go to the lab. Yeah, now we can go to the lab. So this is, I think, a good example. So what we do measure here in terms of results of a trial, in this case the fineness, we take the samples. And we have here a small laboratory where we can analyze the samples. And of course, in terms of fineness. Perhaps you recognize this from the previous Food for Thought sessions, where we did chocolate flow.
So we got here 3 samples. You can look, I put it on a pretty big letters. So the mixer, the first ball mill and the second ball mill. So what operators will typically do is they will measure with a micrometer.
Yep.
Standard is do a same sample for 3 times, then you got your average result. We of course are also equipped with a nice machine, a laser diffraction analyzer to give some nice graphs to give it more like a visualization. Yeah, exactly. So here on the screen we have in the red line we got the mixer. So you see a pretty big lengthy curve. So that means there are all kinds of sizes of particles going around, which is typical for a premix. So you have a lot of different particle sizes. Then the first ball mill already does some real refining. So we start to see the graph coming close to each other because more particles are starting to form the same size.
So basically what happens is those big particles, you refine in the first step to this line, the green line. Okay.
This is not yet where you want to be as a customer because you can still taste particles. Like you maybe know, below 30 microns as a human we cannot taste particles, but above we can. So that's why we do the second part of refining, and that's what you see here is the blue line. So the graph even comes closer to each other. That means more particles coming closer to the same fineness and also to a lower fineness.
Okay.
And this is the fineness we actually want. It depends on who you are, but usually we take about 80% is about the average sample, and in this case it's about 20 to 21 microns. So this is exactly our ballpark.
Our ballpark will be this 21 or 21 micron. Okay.
But let's see if I can match the same results with the micrometer, because this is of course interesting.
Yeah, so typically this is what an operator is doing in production. He takes a sample, he wants to know, am I in the right way, in the right fineness, what I need to go, because for one, if you have an application of a chocolate or a compound, which is, for example, coating a cookie, then in some cases the fineness can be a bit more coarse. Then you can go to 35, 40 microns. But if you want to make a bar out of it, a bar of chocolate, you want to have a smooth chocolate, then the industry standard, typically you want to go to this 20, 25 micron. So an operator wants to know, he takes a sample just like this, he puts a small amount on an hourglass, he dilutes it, because we want to know in a hand micrometer how big the particles are. So.
And this is a foreign oil, so what it does is it goes in between particles that might be stuck together, and then you have more accurate measurement of how big the particles actually are.
If there are some agglomerates in the sample, you will break up the agglomerates, so what you do is measure the individual particles. Now, hand micrometer works in two completely flat surfaces, a bit of a sample in between there, and the biggest particle makes it go, gives the resistance, and then you will have your click, and then we'll have something which is 800 micron.
I have 18. This is the second pass.
Oh, the second pass already. Okay. So this means that in this case the biggest particle is 18 micron. We know, and this is also from those analyses with the particle size distribution, that this biggest particle stands for approximately 82% of all the particles, which means there are some smaller particles, there are some bigger particles, which is normal in any compound or chocolate. So,
correct.
So that's how it works. So measuring by hand, measuring as we do it with the operators, in here measuring with a bit more detail in a particle size distribution curve. What else can we tell about those systems? What is important to understand is what we just showed you was a continuous system, but it's also possible to have a discontinuous system, a batch system, where you can take it from the mixer through the first ball mill and then pump it back into the mixer. And then you circulate over the ball mill until you have the right fineness. Of course, your capacity will be a little bit lower, but your fineness will be okay. So it depends on where you want to go. It's a really flexible system, ball milling. You have a continuous system, a batch system. If you start with a batch system, it's easy to expand to a continuous system. So I think a very flexible solution, a very easy solution, and it will work for any kind of recipe where you have 30% fat or more.
Nothing to add.
This was it for this session. Looking forward to see you all again on the next session with PROBAT Food for Thought sessions.
Right.
Bye-bye.
Bye.